Hi everyone, good morning. My name is Allan and I'm from Engineered. I'm here to talk about autoscaling containers using math. I'm the author of the Docker High Performance book from Packet Publishing. It was released last January, so today most of it is obsolete by now. So, yeah. So I'm a support engineer in Engineered, and we work on days, the Kubernetes Pass, and I work as our customers' extended DevOps teams, helping them debug stuff in production when things are on fire. So today, I'd like to talk about the distributed systems we run in production. So typically, we are an ops person, and we manage a server farm that receives traffic. So let's say we want to keep the utilization at 60%. And so if it's above 60%, our monitoring system, like Nagios, will page us up and wake us up at 2 a.m. in the morning to say, you need to add more instances because because our goal is to be below 60%. So you wake up, log in, provision more instances, or configure something, look at the utilization, and hopefully when things are normal, you go back. Okay? So, however, let's look at your air conditioner. So it looks very similar, wherein you have your thermostat that sets the valve of how it cools your room. And if the room is too hot, the sensor will ping the thermostat to release more cooling elements because it's above our set temperature. So it looks the same, except that your air conditioner doesn't have an ops team that wakes up at 2 in the morning. So what's the difference there? So they're both the same in a sense that you have to configure something. In the case of your air conditioner, the coolant. And in support, I always get these questions of like, how do I configure my application server? How many instances do I need? How much capacity do I need? So from time to time, I tend to refer them to how to manage capacity or tune their performance through this book. It's been useful a lot in my career as well, personally. But looking back at the thermostat, autoscaling, and it goes the same for autoscaling as well, so here you have a Kubernetes horizontal pod autoscaler. You set the number of pods, it configures the replication controller, and the replication controller reports to Hipster or any monitoring system you deployed to utilize to get the utilization and then adjust the number of instances automatically based on traffic. So, but how do you know if your system is effectively autoscaling? So how do you know you have a good autoscaler? How do you know that you're automating effectively? So like 100 years ago, people thought about configuring systems in control theory. So basically, it's a math that analyzes how changes in a system dynamically evolves. So based on this dynamics, you can make feedback loops to your system and make certain corrections to it. And they have developed math that shows how effective your automation is. So it all historically, it goes back to the 17th century, where in the early days of the Industrial Revolution, where we have what they call a centrifugal governor. So basically, it's the cruise control for steam engines during that time. However, how it works or the math behind it wasn't really discovered or analyzed until the 19th century. So I'm not a historian, but I can annotate that for the past 100 years, people have been cargo culting the steam engine. So go back to what a typical control architecture looks like. So you'll find this diagram in textbooks all the time in standard control theory. So you have your target objective. So in Autoscaling's case, what my target CPU utilization is. And then you have your actual utilization, which is the output, which changes according to the either the disturbance, the traffic you're receiving, or the input, like how many instances you set. And then you work them together to set up your feedback loop. So this is an example autoscaling configuration. I think the model's wrong, but I'll still go with it. So here we see that at the start, our target is at around 80% utilization, and we spin up 200 instances. And then at time 3000, we decided we're preparing for an event for our system. So we're expecting a lot of traffic. So we set the target utilization down to 40%. And then the system dynamically responds by provisioning or deprovisioning instances. So here, I don't know why, but it deprovisioned instances. And then at some point at time 6000, traffic spikes. And then, but we still want to maintain utilization of 40%. So our autoscaler will then respond by provisioning more instances, as you can see in the green line. So it had two steps. So we had the regulatory control. We changed our objectives. And then we had disturbance rejection, where we want to have the same performance even though we have noise, where in this case, the traffic of our app. So the nice thing about control theory is that you can model your system in a linear equation, meaning like there's a direct relationship between your input and the output. So here you can have this math equation. Basically, Y is your target utilization, CPU utilization, and then U is the number of instances. So basically, the partial derivative there says that the number of instances you should set is dependent on the change in the CPU utilization and the current CPU utilization. If you go to the digital world or the monitoring system, you can say that my CPU utilization is dependent on the utilization before and the number of instances I set, because there's memory effect on the utilization because you have delay in your monitoring system or the way your server works. So with the math defined, like you can figure out how is your feedback loop effective. In control theory, like if you look at textbooks, there's like 4 nice properties you want. So first, we have stability. You want your CPU utilization to converge to settle to a certain value after time. So here you see that you're provisioning instances, but then you notice that you're over-provisioned, so you deprovision again, but then you deprovision too much, and then so you provision again, but you provision too much, and it goes on, and your system explodes. Similar here as well. Like, so there's probably something very wrong in your architecture that no matter how many instances you add, your utilization keeps going up. And then you have like oscillatory behavior as well, where it just doesn't settle. You keep adding and subtracting instances. So what you want is something that settles down. So this is one that over-provisions and under-provisions instances. And then here you have a nice system that settles for a time. And then you're also concerned about the accuracy of your system, like how far are you from your target utilization in the case of autoscaling. And then you have the settling time. So you want to reach your target utilization in a short time. So in autoscaling sense, you want to provision instances fast enough that you won't lose traffic. So this is why containers are very attractive to explore this idea, because you can spin up instances pretty fast. And then next, we have what we call overshoot. So overshoot in autoscaling sense is you provision too much instances, so your CPU utilization is not your target, so you try to throttle back. So you want, depending on what you want to minimize it as much as possible. But the nice thing when you overshoot is that the math says that you reach your target value much faster. So you pick your trade-offs there. Okay, let's go back to how you implement controllers. So basically, so you have your R of k, which is your target CPU utilization, and then your current utilization. You should track them together to get the error. And then after that, you apply your controller. Simple. So there's a few kinds that are applied. So first, there's proportional control, where your number of instances is proportionally related to the difference in your CPU utilization, which is found here. Some math properties, they're inaccurate, but like they get the job done 80%. So increasing the proportional ratio makes you have a higher overshoot, and settling time is longer as well. So then what you can try to do is you can average out your measured values using an integral controller, where you're dependent on the previous value you set, or the number of instances times the error. So here you improve the accuracy. However, since you're averaging over time, you're increasing the settling time of your controller. So your autoscaler responds very slow. So another one that's nice in math is the derivative control, where you check the rate of how your error changes, so you can project how many instances you'll set in the future. So it's nice because it responds fast, but since you respond fast, but then you'll be very sensitive to noise because you look at the sudden changes in your system. So all these nice linear controllers are useful for a certain case. However, you can have non-linearity in your in your model as well. So here you have if you increase the number of instances, your utilization increases proportionally. It looks weird. But the point is that at some point, adding instances doesn't help your application. Like the utilization is still the same. Things are still on fire because the problem is probably somewhere else, like your database or load balancer. So with that, I'd like to end about control theory is a model to iterate on your feedback loops, and having a model for your feedback loops helps you identify how effective is your feedback loop with the categories I showed earlier. And then next is that linear models can get you a long way in describing the effectiveness of your systems. However, like in DevOps or Agile, where you put your feedback loops, you need to keep evaluating your models if they are really effective for your applications, because it's a continual process of having a model and then having a model continuously learn by itself using machine learning or control theory. So if you want to get started on control theory, these are nice, useful books. So this O'Reilly book by Philip Jannert gives a nice introduction, and it has Python simulations you can start with. This other book by Joe Hellerstein and others, like they were a bunch of researchers in IBM when this book was written. It had sample case studies of systems that you can auto-configure. So control theory doesn't only work for auto-scaling systems, it also works for getting the correct configuration for your application. So in the blue book, they have mentions like how to get the optimal Apache Max client setting to improve CPU utilization and memory usage and all that. So in general, control theory is not only for autoscaling, but it's a nice way to evaluate your feedback loops. So that's it. So at Engineer, we have a raffle tomorrow if you want. And my control theory notes is in my GitHub account. So thank you, everyone. Do you have time for questions or?
Have you looked at, or is part of what control theory on cybernetics at all?
Yeah. So actually, if you look historically, control theory has deep roots in cybernetics as well. So if you go like more advanced in control theory, like especially with nonlinear models, there's like fuzzy control. So if you study traditional electrical engineering in control theory, you look at like controlling robots, like how the segways work, those kind of things. So it's a good background as well. So the model I presented is mostly for digital signals and signal processing because they're useful because your monitoring systems are sampled from time to time. So the model works better this way. Okay, yeah, thank you.